Welcome back to this video series where we continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular, in this video, I'm going to talk about some concepts discussed in Chapter 8 on LMI-based controller designs and anti-windup designs. And here we start with a quick motivation in terms of the linear system x dot is equal to ax. And we want to characterize asymptotic stability or exponential stability properties of the origin. Then we know that the origin of this system is exponentially stable if we can take an arbitrary positive definite matrix Q, and then there must exist a positive definite matrix P satisfying the Lyapunov equation here. Because based on this solution of the Lyapunov equation, we can define a quadratic Lyapunov function. And with that Lyapunov function, we looked at the derivative v dot of x of t. And that was then telling us, well, we have a decrease, meaning v dot of x of t is less than 0 for all x unequal to 0. Providing a verification of exponential stability. Now, what we are actually interested in is really just this decrease, meaning v dot of x of t being less than 0. But the matrix Q and the matrix P are maybe not that important, or it would be nice to have them as a design parameter. So instead of looking at this Lyapunov equation, we can also look at this linear matrix inequality, or these two matrix inequalities, where now the inequality sign has to be understood in terms of the finiteness of a matrix. And if we want to translate the condition of the Lyapunov equation, then we can say, well, we are looking at for a positive definite matrix P, which needs to satisfy additionally this inequality in combination with the matrix A. So here the matrix Q is not present, meaning Q can be considered as an additional degree of freedom, and then one might hope that one can get optimal Qs or optimal Ps, where optimality has to be understood based on the corresponding application. Okay, but how could we solve such a set of linear matrix inequalities? Well, as a first step, we can rewrite them as convex optimization problem. So this is just one way one could implement that or rewrite that by saying, well, let's minimize a positive parameter k, so have an optimization problem in a parameter k and the unknown matrix P subject to certain inequality constraints. Meaning we want to have k positive. We also want the matrix P to be positive. That's encoded here in the second constraint because it can be rewritten as alpha times the identity matrix being less than P, and alpha is a parameter which we can select and keep as a constant. The next parameter that would try to ensure here that P is not too large, meaning we can rewrite that as P is less than K plus alpha plus the identity. So we try to minimize this parameter K here such that these two conditions are satisfied, and the last condition is simply the decrease condition here needed for the decrease of the Lyapunov function. Okay, well, that's a convex optimization problem, but how do we actually solve it? Well, for these kinds of problems, there exist tools For example, in MATLAB, one could use the toolboxes CVX, SOS tools, or YALMIP to write optimization problems of this form and then solve them. Or I should better say approximations of this optimization problem, because to actually solve them, it is better to rewrite the inequalities here in inequalities of this form, so having less or equal to, and to make sure then that still this optimization problem here is satisfied, we can introduce a small parameter epsilon and add it in the corresponding equations where necessary. Okay, so here we haven't reached the main concept of the chapter yet, but this is supposed to show how linear matrix inequalities can be used to potentially design Lyapunov functions for linear systems. So as a next step, we make the setting slightly more complicated and look at a linear system of this form here. Now a system with output Z and with disturbances W. What we have seen in as a first step, if we ignore the disturbance, setting the disturbance W equal to 0, then we get what is also known as so-called internal stability or zero global asymptotic stability. 0 here referring to W being equal to 0. And yeah, as before, we can verify if the origin is globally asymptotically stable either by checking the eigenvalues of the matrix A or by constructing a quadratic Lyapunov function. What we've seen in the chapter in chapter 7 using input to state stability was that we could also come up with a certain bound on the state depending on the possible disturbance W. So by more or less redoing the calculations done in the ISS chapter, by considering a quadratic Lyapunov function with a very specific selection of the matrix Q, we could come up with this chain of inequality here, giving us a bound, an L2 bound of the signal X, depending on the disturbance W and depending on this parameter gamma here. Meaning we want to optimize the L2 gain gamma such that we have a bound on the state X with respect to the disturbances W. Or if we slightly modify that to actually take also the output into account now, then we can use a slight modification of the calculation in chapter 7 and simply kind of say, well, can we find a matrix P, again a positive definite matrix P, such that the derivative along the quadratic Lyapunov function, so being the same form as over here, satisfies the corresponding inequality here. Using then similar steps as before, one can show that this also again then implies global asymptotic stability of the origin under the assumption that no disturbances omega W are present. But similar as the bound over here as well, having now a bound in terms of disturbance W and then a corresponding property on X, we can translate that to a bound on the output of interest Z and and the disturbance W. And yeah, the bound simply then follows by integrating the inequality we have up here. So remaining question that we would have here would be, can we compute a positive matrix P and a parameter gamma by solving a linear matrix inequality, namely a form of a matrix inequality as visualized here, to establish a bound of this form here. Well, and for that, we need the tools of linear matrix inequalities and being able to solve these linear matrix inequalities. And the first inequality here is simply copied from the previous slide. Rearranging terms, we can get it in this equivalent form. And now if we isolate the vectors x and w on the left and the right side, well, we end up with a third expression here. We are now, this is really just a scalar inequality, but as before, if we want to write that as a linear matrix inequality or a matrix inequality, then we remove our vector x and w on the left and right, and we are left with this matrix inequality here. Now let's recall what the unknowns are. So we said we are interested in finding gamma and p, but if we inspect these different components here, well, we see here the unknown p. That's all fine. They appear linear. So here we recover essentially the component of the Lyapunov equation, and then it also appears linear in the term p times e, or e transpose p. But the factor gamma appears once with gamma times I and then 1 over gamma. So gamma is not a linear component here. Meaning, focusing on this first bit here, for a fixed gamma, we could solve this as a linear matrix inequality in the unknown p, and then obtain a positive definite matrix if the matrix inequality here is feasible. If we also want to optimize gamma, then we first have to rewrite that matrix inequality here. And there is a common trick which is then applied many times in papers using linear matrix inequalities to end up with a formulation that can actually be solved by one of the tools in MATLAB, for example, and that's the Schur complement. There are other techniques, some of them also discussed in the book, for example, the S procedure, but these are two very common, let's say, tricks used in proofs on matrix inequalities to obtain a representation of matrix inequalities that can be solved by standard software. So what is the Schur complement mentioned here on this page? Well, the Schur complement gives me an equivalent representation of matrix inequalities. So if I have this matrix here consisting of Q, S, and R of dimensions such that we can build this bigger matrix, then that being negative definite is equivalent to these two conditions here, meaning R negative definite and this inequality here being satisfied. And we can apply this trick. So here we also see that essentially R appears once as an unknown r, and then as an unknown r inverse, similar to the factor here gamma, meaning we can rewrite the matrix inequality here on the left in the following form, taking r equals to minus gamma, summarizing the matrix C and F in this term S, and then this allows us to equivalently represent the condition here through the condition here, where we additionally assume, well, that gamma is positive, meaning minus gamma is equal to r is negative or negative definite. And here now we observe that the unknowns, namely P and gamma, appear only linearly, meaning we have defined a linear matrix inequality, which we can solve through standard software, which allows us to, if we quickly go back, which allows us to get this input-output relationship between a bound on Z in terms of the L2 norm and a bound on the disturbance W in the L2 norm. This was just a simple example discussed in the chapter, and that can be extended by applying the Schur complement multiple times, by applying other tricks as mentioned, the S procedure, and that with this technique more complicated systems can be analyzed. So here is a more general system consisting of a plant. So the plant here would represent a linear dynamical system with an internal state xp, but also having then this output of interest Z and this disturbance W. We can design an output feedback controller, so using the output Y here in a controller with its own dynamics to define a controller. That controller might have constraints in terms of saturation, leading to this overall closed loop system here, represented through the two components, plant and controller, or equivalently represented through the system here, compactly written with more complicated definitions for these individual components. And with this, then we are able to analyze properties for this particular setting and design, in this case, different components of this system in such a way that we have asymptotic stability, local asymptotic stability, global asymptotic stability, disturbance rejection, and can take these nonlinearities in terms of the input into account. Okay, and this concludes the video here on chapter 8, and in the next video we continue with control Lyapunov functions.